Jupiter's auroras, the JWST discovery that shouldn't exist. NASA's James Webb Space Telescope pointed its infrared eye at Jupiter in 2024 and saw something impossible. Not the slow, majestic curtains of light we've observed for decades, but flashes, rapid, pulsing bursts of energy erupting by the second, hundreds of times brighter than Earth's auroras, changing faster than any ever recorded, and glowing in wavelengths that shouldn't exist. JWST's near-infrared camera detected light at 336 microns, a wavelength invisible to every previous telescope. And what it found didn't just challenge our models of Jupiter, it broke them. When Hubble looked at the same moment, in ultraviolet light, some of the brightest infrared bursts weren't there. No UV counterpart, no matching signature. As if two telescopes were seeing two different worlds, occupying the same coordinates in space. Three questions emerged. What mechanism can make auroral light flicker every second on a planet 318 times Earth's mass? Why do these infrared emissions appear without ultraviolet light, breaking every model of auroral physics? And what unknown energy source could be heating Jupiter's upper atmosphere beyond what our equations predict? The universe had just handed planetary scientists a riddle, and JWST was the first to catch it in the act. Auroras happen when charged particles slam into a planet's atmosphere, energizing atoms and molecules that release light as they cool. On Earth, that's solar wind. On Jupiter, it's more complicated. Jupiter's magnetic field is 20,000 times stronger than ours. Its magnetosphere, the bubble of magnetic influence surrounding it, is the largest structure in the solar system. If it were visible from Earth, it would appear bigger than the full moon. According to NASA's Juno mission, Jupiter captures not only solar wind particles, but also ionized gases erupting from its moon Io, the most volcanic body in the solar system. Every second, Io spits a ton of material into space. These sulfur and oxygen ions become trapped in Jupiter's magnetic field, spiraling toward the poles and igniting permanent auroras that never stop glowing. But JWST saw something no one expected. Instead of steady light, the auroras flickered. Individual bursts appeared, doubled in brightness, then vanished, all within seconds. Temporal variability on sub-second timescales. Dr. Jonathan Nichols from the University of Leicester called it a complete rewrite of auroral physics. Previous models predicted changes over hours. JWST saw them in heartbeats, and then came the mismatch. Infrared flares with no ultraviolet signal. On Earth, every aurora emits a blend of visible, UV, and infrared light, different colors of the same phenomenon. Jupiter's new auroras glowed in deep infrared, and nothing else. It's like finding a fire that gives off heat but no visible flame. The physics shouldn't work, and yet there it was, blazing across Jupiter's poles with the intensity of a small star. Two explanations dominated the early debates. The first, magnetospheric turbulence. NASA's team proposed that violent magnetic reconnection events, similar to solar flares, were accelerating electrons to near-light speeds, creating rapid bursts of infrared energy. This theory fits the brightness and speed, but the energy required would drain Jupiter's magnetic field in days. The math doesn't hold. The second, eoplasma injections. Perhaps eruptions on Io flooded Jupiter's magnetosphere with exotic particles, triggering energy cascades toward the poles. But Io's activity remained steady. A new hypothesis emerged: wave-particle interactions. In Earth's magnetosphere, electromagnetic waves, called Alphen or Whistler mode waves, can resonate with charged particles, accelerating them to extreme energies. It's like pushing a swing at exactly the right moment. Small pushes, huge results. Now scale that to Jupiter. A magnetic field tens of thousands of times stronger. A 10-hour rotation spinning magnetic lines like cosmic tornadoes. Under such conditions, these waves could accelerate electrons with unprecedented efficiency, producing the flickering, high-energy bursts JWST captured. And depending on the wave's angle and polarization, these interactions could excite infrared-emitting ions without generating the usual ultraviolet light. That would solve both mysteries, the rapid variability and the wavelength mismatch. But there's a catch. We've never directly measured those waves at Jupiter. No spacecraft has flown through that region. Juno orbits too far south. Cassini passed by too quickly. For now, the mechanism remains theoretical, a plausible solution waiting for proof. Another frontier idea goes even deeper, into quantum atmospheric chemistry. At extreme ionization levels, molecular hydrogen doesn't behave normally. Quantum simulations show that under electron bombardment 1,000 times stronger than Earth's, H2 can fragment and reform into unstable ions that radiate only in infrared. That could mean Jupiter's auroras are powered by chemistry that no laboratory on Earth has ever reproduced. These are natural but exotic processes, occurring under pressures and magnetic fields we can't simulate. And that's what makes them so fascinating, because every new observation seems to reveal not just how little we know about Jupiter, but how limited our physics still is. It began with a flicker, a few strange bursts of light at the edge of infrared detection. But what JWST found may represent the most complex electromagnetic system ever observed in our solar system. Magnetic turbulence, volcanic plasma, wave-particle interactions, quantum chemistry, all working together in a dynamic symphony of energy, motion, and light. Each theory explains part of the picture, but none explain it all. And that's the beauty of it, because every unanswered question expands the edge of what's possible. Jupiter's auroras might not be a mystery to fear, but a message from physics itself, reminding us that the universe is still far from fully mapped. Over the next decade, 3 missions will chase these answers. NASA's Juno will continue its polar passes through 2025. The European Space Agency's JWST mission arrives in 2031, equipped to measure magnetic fields, plasma waves, and infrared emissions right inside Jupiter's magnetosphere. And JWST will keep watching, searching for patterns in those flickers, tracing the heartbeat of the solar system's largest planet. The mystery isn't solved, but it's alive. And that's exactly what makes it worth studying. If auroras can flicker faster than thought, if light can exist without the wavelengths we expect, what else might the universe be doing just beyond our perception? The cosmos keeps its secrets, but it also leaves trails of light for those willing to follow. Subscribe to explore them with us, because the deeper we look, the stranger and more beautiful the universe becomes. In Cosmos we trust.